happen. It's the case where the singularities, the bad points, all have winding number plus or minus 1, corresponding to gapless modes of positive or negative chirality. Now, how does one prove the sum of the winding numbers is 0? I'm going to give 3 versions of the explanation. The third one will be closest to what Charlie said. Well, perhaps I should say that, well, they're all pretty close to what Charlie said. The reason I'm going to give 3 different versions is that since it's kind of an important point, it's good to be familiar with it from several points of view. But I won't have time to go through all 3 versions in equally detail. But I'll be rather brief with some of them. So one rather down-to-earth explanation is as follows. The winding number for a map from S to the 2-sphere n equals 1 can be expressed as an integral formula. So this is a very beautiful formula. You have n, which is a function of p, and you can compute the winding number by integrating something over the sphere. So this integral is supposed to go over the 2-sphere S. I should have written an S down here. And what you integrate is 1 over 4 pi times an explicit function of n of p. So mu and nu are the components. So what is meant by du is d by dp mu. But the derivative is taken tangent to the sphere S because this formula is defined entirely on the sphere S. So that's a completely explicit formula for the winding number as an integral over the sphere. And by the way, from this definition, it's not hard to check what I told you before, that if n is p or minus p, then the winding number is 1 or minus 1. Now, here's another way to write the same formula. I wrote it 2 different ways because I wasn't sure which one of either would be clearer. Okay. So here I wrote it in terms of a triple cross product of the vector n with its derivatives, and here I wrote that explicitly using an epsilon symbol. I considered a few more ways to write this formula, but I decided to just write it twice and hope one of them was clear. Now, there's a very useful fact. If we take the integrand here and differentiate it with respect to p, we actually get 0. You see, if I take d lambda to act on one of these n's, I'd get 0 because I'd have a second derivative, which is being anti-symmetrized because of the epsilon symbol. But if the derivative acts on this first n, then we get 0 for another reason, which is that since n lies on a unit sphere, its derivative is normal to the unit, is a normal vector. And a tangent vector to the sphere, normal to n itself. And the space of vectors which is normal to a given vector n is only 2-dimensional. N lives in 3 space, but vectors that are perpendicular to n are only a 2-dimensional space. And here we're taking a triple cross product of 3 vectors that are all perpendicular to n, so that triple cross product is 0. The 3 vectors are linearly dependent, so their triple cross product is 0. So that's an explicit identity. And now we're going to use it. So we'll use it as follows. For each bad point P alpha, we let U alpha be a small open ball around P alpha, whose boundary is a sphere. And then we're going to remove, so I've drawn here the full Brillouin zone, and then I've drawn the bad points. And then I've drawn a little open set U alpha around each bad point P alpha. And we remove those bad points to get a B prime. B prime is the Brillouin zone with some bad points, well, not just bad points removed, but little open balls around the bad points have been removed. And I didn't write it on the picture, but the boundary of each U alpha is a sphere S alpha. And now we're going to use Stokes' theorem. Stokes' theorem on the 3-manifold B prime. I noticed from the questions Charlie got, however, that people were confused about Stokes' theorem. And therefore, I don't know how to state this in a way that can't potentially invite confusion. Stokes' theorem in general is a theorem on any manifold with boundary. For us, the manifold with boundary is B prime, and its boundaries are the boundaries of the U's, which I've called the S's. And it's true that in the picture, it looks like B prime has other boundaries, but those boundaries are really glued together. So B prime doesn't have boundaries there. Right? The boundary of B prime is only the S's, these little green spheres, which are boundaries of U's, but also they're boundaries of B prime. So we're going to do Stokes' theorem on B prime. So the identity we had before was that this expression is 0. So it's 0 even before we integrate over B prime, so it's certainly 0 after we integrate over B prime. And now we integrate by parts on B prime, but when we integrate by parts on B prime, we pick up surface terms, but the only surfaces or boundaries are on the S alphas. And what the boundaries are, well, when we integrate by parts, we remove this derivative, and we're left with this expression, which means that the surface term on S alpha is the winding number on S alpha. So we've learned that the sum of the winding numbers is 0, as promised. Now, that's my first derivation of this formula. I'm going to go through the second derivation I won't go through as systematically. I'll express it in a more abstract language. I only have one slide on it. It'll be clear to you if you are familiar with some relevant facts about differential forms. If you're not, then you might just bear in mind as something you might eventually want to learn, because it leads to a more streamlined version of this proof I've just given, and of some other arguments. So if the next slide is not clear...
Excuse me. A question from Karen. So I don't quite understand the first step. So why the integral inside on the interior of B prime is 0?
Even before we integrate, this expression here is 0. That's what we proved back here. This is 0. So,
okay.
So what we're integrating is 0.
Okay, I see. Thank you.
So one integral we know how to do is the integral of 0. So if you're familiar with differential forms, you can give a more elegant statement of what I've just said. We write S sub n for the two-sphere where n is 1 in absolute value. Sorry, I left out the absolute value sign here. And then this two-sphere has a volume form that I'm calling eta. It's a closed form. Well, it's closed because we're in 2 dimensions, so a 2 form is going to be closed. And its integral over S of n is 1. And now we have a map phi from S to Sn, and the winding number is defined as the integral over S of the pullback of eta by phi. And since d eta is 0, phi star of d eta is 0. So what we integrated, in the previous derivation, what we integrated was 0. But the thing which is 0, I'm now writing as phi star of d eta. And then, if you know your differential forms, you can pull d out of the statement. So the integral of d of phi star of eta is 0. And then Stokes' theorem would turn that into this. And that's the sum of the winding numbers. So if you're familiar with the mathematical notation and terminology I used in this page, you might recognize that it's the same as what I said before. I said it before in the more explicit language, just because I didn't want to assume that one was familiar with this language with differential forms. Also, I was asked by someone about 5 or 8 minutes ago why I said it was more natural for the Nielsen-Linear theorem to define the winding number in homology rather than homotopy. The answer is perhaps not clear because this computation we did is in homology and is not really natural in homotopy. Now, there's another way to describe what we've just done, which involves the Berry connection. And you see, more fundamentally, before you talk about the Berry connection, you should talk about the line bundle on which the Berry connection is a connection. So for each value of p away from the bad points, the Hamiltonian h of p has one negative eigenvalue. So the space of filled fermion states of momentum p is a one-dimensional complex vector space that I'll call L sub p. And a vector in L sub p is a wave function that obeys h of p times psi sub p. I wrote here -1, but it should be minus epsilon of p times psi of p. It's an eigenstate with negative eigenvalue. The fancy way to say this is that as p changes, you define a complex line bundle whose fiber at P is this L sub P. Now, how precisely can we say what we want psi sub P to be? We can ask for psi of P to be normalized. So we can ask for its norm to be 1, but there's no natural way to fix its phase. However, suppose we vary P continuously by a path P equals P of S from, say, P1 to P2. So S is some parameter, and we think of P as a function of the parameter S. We're at the initial value of S, we're at P1, and we end at P2. You can think of that as a path that lies in a sphere P minus P star equals epsilon around the bad point P star. You don't have to think of it that way. It could be any path in the Brillouin zone away from bad points. But it's fair, since the behavior near a bad point is interesting, it's natural to think of this as a path in a little sphere near a bad point. Now, there wasn't any natural way to pick the phase of psi sub P at P equals P1. You can pick a phase, but there's no natural way to pick that phase. But if you do pick any phase at P1, then you can parallel transport the phase along the given path by requiring that at all P along the phase, d by ds of psi sub P is orthogonal to psi sub P. Now, I'm going to explain in two ways the fact that this uniquely determines the S dependence of psi sub P. Well, maybe I'll just explain it in one way. The fact that the first condition on psi of P is that for all S, psi of S, is that for all S, it's supposed to be a negative eigenvalue of H. So what freedom would that leave in d psi ds? Well, that alone would allow us, when we change S a little bit, to add to psi a multiple of psi. Because when the momentum changes, we have to change psi, or else it wouldn't remain a negative eigenvalue of P, of H. But if we add to psi, the freedom when we evolve psi is that at each step you might add to psi a multiple of what it already was, a multiple of the negative eigenvalue you had. So to fix the S dependence of psi sub P, you need to decide to what extent d psi ds has a term that's proportional. D psi ds at a given value of S, let's say S0, is proportional to psi at S0. So the part of d psi ds that's orthogonal to psi is uniquely determined by asking that psi is an eigenstate of the Hamiltonian for all S. That condition wouldn't determine the part of d psi ds that's not orthogonal to psi. And we fix that part by saying that we want d psi ds to be orthogonal to psi. So if we say that psi p is supposed to be for all S an eigenstate of the Hamiltonian, and moreover it's supposed to obey this condition, then that determines uniquely how psi depends on S. Concretely, the real part of the equation ensures that psi p has a constant norm along the path, and the imaginary part determines how the phase of psi p depends on the parameter S. So, to recapitulate, well, psi lives in a two-dimensional space, so it's going to take two complex conditions to determine d psi ds. One complex condition is determined by saying that psi is always an eigenstate of H with negative eigenvalue. That only determines one condition because H has a one-dimensional space of negative eigenvalues. So we need one more complex condition, and it's this one. That's the second condition that determines d psi ds uniquely. So our two conditions that determine d psi ds are that it's always a negative eigenvalue of H and that it satisfies H. With these conditions, psi is uniquely determined along the path and will automatically remain normalized if it's initially normalized, and we have a unique recipe to evolve its phase. Now, having a rule of parallel transport of the phase along any path amounts to defining a connection Well, people often abbreviate by saying it's a connection on B prime, where B prime is the Brillouin zone with bad points removed. But a better mathematical language is it's a connection on the line bundle over B prime, whose sections are the negative eigenstates of H, the sections that are being parallel transported. But if you're confused about the phrase in parentheses, drop it and just call it a connection on B prime. A connection is the same as an abelian gauge field. And I'm going to call this abelian gauge field curly A, because I use straight A for the vector potential of electromagnetism. So this connection is the Berry connection. What we've just defined is the Berry connection on the space of negative eigenvalues of H. Now, if we make parallel transport around a closed loop gamma, psi will come back to itself with the same norm, because the Berry connection preserves the norm, but it won't necessarily come back to itself with the same phase. The Berry connection isn't flat. So parallel transport around a closed loop using the Berry connection doesn't bring us back to the starting point. It changes phase. The Berry connection has a non-trivial curvature, F, curly F I call it. So I call the Berry curvature curly F because straight F will be the electromagnetic field strength. So curly F equals dA is the curvature of the Berry connection. If we divide this curvature by 2 pi, we get the first Chern class of the line bundle of negative states, negative eigenstates of the Hamiltonian. Now, if P alpha is one of the bad points at which two bands cross, and S alpha is a small sphere around P alpha, then the flux of F over 2 pi is the winding number as defined earlier. Well, why is this true? Well, one answer for why it's true is that Berry showed it in his original paper. He computed the Berry curvature, and the Berry curvature was, well, any of these expressions we had some time ago. So the integrand here or here is the Berry curvature in this situation. So I gave the derivation without introducing the Berry connection because we really, that in the two-band case, that expression was so elementary, we could define it by hand without knowing it is the Berry connection and curvature, and that's what I did. But a reinterpretation of what we said is that the integrand was the Berry flux, or the curvature of the Berry connection divided by 2 pi. And when you have this reinterpretation, then it's natural to repeat the derivation we gave before. So the Bianchi identity for any abelian gauge field, such as the Berry connection, tells us that dF is 0. And so again, we got the Nielsen-Minamia theorem. So it always comes from integrating 0. There are just different ways of explaining what is the 0 that's being integrated. So in this formulation, 0 is the left-hand side of the Bianchi identity. We integrate 0 over the Brillouin zone with the bad pieces removed. And Stokes' theorem says that that's equal to the sum over the boundaries of the Berry flux over the given boundary. And that's the sum of the winding numbers.
So when you say bad points, basically poles of the Berry connection?
Well, they're poles of the Berry connection, but I think it's more physical to say that they're points where the bands cross. So we have to have a note. What I've called bad points are the points where the two bands cross, where the Hamiltonian has degenerate eigenvalues. At that point, we can't define the line bundle on which the Berry connection is supposed to be a connection, because that line bundle has for its fiber the one-dimensional space of negative eigenstates of H, and there isn't such a one-dimensional space where the bands cross. So the line bundle on which the Berry connection is a connection isn't defined at the bad points. You can say that the connection has a pole there, but that's putting the cart before the horse. The Berry connection is a connection on a line bundle that isn't defined there. And it's not defined there because there wasn't a negative there wasn't a valence band. There wasn't a negative eigenstate of the Hamiltonian. So I'm not going to give any more derivations for this, so this is perhaps the best time for a question if there's one.
So it seems that this theorem now holds for all basically odd numbers of spatial dimensions.
Well, Well,